All right, so we have notes for section 8.4, which is the lengths of curves. So example 1 was the length of the curve y equals sine x from x equals 0 to x equals 2 pi. So what actually happens, if you think about this curve, it's just going to look like this. So what I'm going to do essentially is approximate each section of the curve as the hypotenuse of a right triangle, which is some change in x squared plus some change in y squared. So those are my legs. Now the problem is I can't sum these up, but what I can do if I want to get them in the right form is essentially I need to add up all of these lengths along the curve, but I want these values to go to 0. Now what I can do though is I can do this, delta x squared plus delta y squared all over delta x and multiply it by delta x, and now it looks like a sum of something that I can add up. Now this can be simplified because if I square this guy, I can put him underneath the root as well. So that becomes this delta x squared over delta x squared plus delta y squared over delta x squared delta x. Well, that's 1. That's delta y over delta x all squared. So I have this. Now, it's the same thing as this. So this is the derivative. So that's y prime squared dx. So there's my formula. So to find the length of this curve, I need y prime, which is the cosine of x. So the formula for the length of the curve from 0 to 2 pi, 1 plus the derivative squared dx. Now this is not something that I want to, evaluate, so we're just going to let our calculator handle it. So the square root of 1 plus the quantity cosine x squared from 0 to 2 pi, and we need to make sure we are in radian, okay. And this comes out to be about 7.64 units. So the length of your curve is that. So here's our formulas. So length of the smooth curve begins at AC and ends at BD. So A is less than B, so A has to be left of B. C less than D, so C is below D. Then the arc length of the curve is given by this. If y is a smooth function on x, or if x is a smooth function on y. So if you notice a slight difference, this uses x values as the bounds. This is the derivative I prime. This is the y values are bound, that's x prime. So find the exact length of the curve, y equals 4 root 2 over 3, x to 3 halves minus 1, from 0 to 1. So let's see here. So we need to find y prime. So y prime equals, so 3 halves is going to multiply out front, so that's going to be 12 root 2 over 6. Subtract 1 from the exponent, half, the 1 goes away. So this is actually 2 root 2 x to the half, which is actually 2 root 2x, because that x is also underneath the root. So from 0 to 1, the square root of 1 plus the derivative squared. So, and then that also goes in my calculator, because that's a garbage thing to try to evaluate. Square root 1 plus quantity 2 square root 2x, close quantity squared, from 0 to 1. So this length is about 2.17. So there you go, which is actually, if you want exactly, it's 13/6. Okay, so sample 3 here. Find the length of the curve y equals x to the 1/3 between -2, all right, -8 comma -2 and 8 comma +2. So, the issue here is that if I try to take, or look at the graph of this, I get a vertical tangent, actually badly drawn, x equals 0, which means I can't use this form. I have to change it around. So x equals y cubed. So x prime is 3y squared. So when I go to do my length equation, square root of 1 plus 3y squared squared dy, my bounds are y values since my variables are y. So it's going to run from -2 to +2, not from -8 to +8. So this will eliminate the issue that the derivative doesn't exist at a location. So and then we go to int. So the square root of 1 plus quantity. Now remember, your calculator though doesn't care what variables you use, so you can still type them in as x's. Just need to remember that your bounds are y's. So this comes out to be about 17.261. All right, find the length of the curve, y equals x squared minus 4, absolute value x minus x, from x equals -4 to x equals +4. Okay, so the issue here is, once again, we're going to have a weird corner or cusp if you look at the graph. If we graph this guy, you got x squared, oops, minus 4, absolute value of x, minus x, draw. So I've got a cusp there at 0, which means I need to break my lengths into two separate equations. Now, the trick here is let's see here. So this is going to be x squared plus 4x minus x. And you also have to do, since the absolute value could be positive or negative, you'd also have to try this guy. So x squared minus 4x minus x. So I actually have two equations. So I have x squared, whoops, I don't know where that 3 came from. It should be minus x. So plus 3x. Over here I have x squared minus 5x. Now for this one, I used a negative x, so this is good when x is less than 0. This one I used a positive x, this one's good when x is greater than 0. So you have to split your absolute value into two functions. Use a negative x and a positive x. So what that means is I actually have two length curves. So for the length of this section, this one only goes up to 0. So my bounds are going to be from -4 to 0, and that's actually going to find the length of this left-hand parabola. So it's going to be the square root of 1 plus the derivative is going to be 2x plus 3 squared dx. So the total length is to add on this one. Well, this one's going to start at 0 and go up to 4. This is the length of the right-hand loop. Square root 1 plus, so the derivative of this guy is 2x minus 5. Now I can work them out. I'm actually going to type this in all at once if I want to. So, square root of 1 plus the quantity 2x plus 3 squared from -4 to 0 plus square root of 1 plus 2x minus 5 squared from 0 to 4. Calculator says the total length of this curve is 19.56. And that is the end of the section.